Hi everyone, I'm Malcolm. In this video, I'm going to work through building user interfaces for your Arduino projects with MegunoLink's interface panel. The interface panel is one of many MegunoLink visualizers you can combine to build and adapt a custom interface as your project evolves, without spending a lot of time wiring switches and dials. I'll work through both the MegunoLink and Arduino sides using this robot gripper as an example. The gripper is driven by a servo motor and has a force sensor on one finger. We'll see how the interface evolves as we go from figuring out where to move the servo to open and close the jaws, through to investigating the response of the force sensor. Along the way, I'll cover serial commands, building interface panels, storing configurations in the Arduino EEPROM, updating the MegunoLink user interface, and plotting. I won't go into every detail in this video. Check out our online documentation to dive deeper. You'll find the Arduino code and MegunoLink project for the gripper controller on GitHub. Links are in the description. And please like the video if you find it useful. It helps other people find our content. An interface panel visualizer is built using MegunoLink's Visual Designer from our toolbox of components and controls. Things like buttons, numeric inputs, gauges, sliders, text inputs, and indicators. MegunoLink sends serial messages to your Arduino program when you use the controls. What the Arduino does with these commands depends on your project. It could update some configuration, move a servo, or start a measurement. Or even send commands back to MegunoLink to change the user interface, updating control values, appearance, or visibility. It is completely up to you. Let's start with some Arduino code to move the servo. I don't know what positions open and close the jaw, so I'll start with a program that moves the servo to an angle provided in a serial command. Using serial commands saves me from wiring up a pot or some other controller. MegunoLink can send messages in any format. If you've already implemented a protocol for your project, feel free to stick with that. Otherwise, we've included a simple command handler in our Arduino library. It decodes serial messages like this. So that's the format I'm going to use today. Just check out our Arduino integration docs to get the library installed. Incidentally, our Arduino libraries have LGPL licenses, so you can use them in commercial projects. Once our library's installed, include the command handler in your Arduino sketch and create a command handler variable. The command handler's job is to receive characters from the serial port, gather them into a complete message, look up the command, then call the corresponding function in your Arduino program. Make sure to include the pointy brackets, otherwise it won't work. In the setup code, register the command using add command. Give it the command text and function name. This links a command in a serial message to an Arduino function. I'll implement the function in a minute. First, add a call to process inside your loop. The process function actually reads the characters from the serial port as they arrive, looking for registered commands. When it finds one, it calls the registered function. So, let's look at the definition for our command handler function. This function is going to move the servo to the position sent in the serial message. All command handler functions need this parameter. It gives the function access to any arguments in the serial message. You need it even if the serial command itself doesn't have any parameters. Raw position messages do have a parameter, the gripper position. So, this function reads that value as an integer. There's a bunch of these methods to retrieve parameters as different types. Check out the command handler documentation for details. Next, the value is checked to make sure it is a valid position before updating the servo position. This function gets called every time the Arduino receives the setRawPosition serial command. So, let's look at sending the command from a MegunoLink interface panel. The interface panel has two views, a runtime view and a design view. In the runtime view, I can enter values into controls and click buttons to send serial messages. In the design view, I can add controls, set properties such as background color, text alignment, or control name, and reorganize the layout. Back in the Runtime view, clicking the Designer button opens the Designer for editing the interface. While in the Designer, clicking Apply updates the Runtime view. But let's start from the beginning. Select the Interface Panel template to quickly start a new project with a Connection Manager, Monitor, and Interface Panel ready to go. Open the Designer. The design surface is in the middle. This is where we lay out the interface panel. On the left is a toolbox with a palette of controls to add to the design surface. On the right is a Property Explorer. Properties change the appearance and behavior of controls. At the bottom is a code example window. We'll come back to that later. Let's get started with an interface panel to test where the gripper ends up at different servo positions. Drag controls from the toolbox onto the design surface. I've added numeric, button, and label controls. The numeric control is for the servo position, the button will send a position command to the Arduino, and the label will help keep track of things when we add more controls. Select a control to set its properties. First, I set a name for each control, so I can refer to it later. Then text properties for the button and label. And finally, the limits for the numeric control. I'll use the normal range for a servo, so we can test all positions to see what works best for the gripper. There's lots of other properties too, but we don't need most of them now. We will need the buttons on click send property though. This property sets the serial message sent when the button's clicked. You can enter the message here, or click the ellipsis button to open the command editor. The command editor helps build and test serial messages. Messages are made up from plain text, expressions, and escape characters. Escape characters begin with a backslash. They're used to add non-printable characters, like carriage returns. Expressions go inside square brackets. You can use expressions to include values from controls on the interface panel and perform simple calculations before sending messages to your Arduino program. Use the pop-up menus to insert common escape characters and control values. Okay. Let's build a command to send a servo position to the gripper controller sketch. Our command handler expects commands to begin with an exclamation mark, followed by the command name registered in the Arduino program. Next comes the parameters. Here there's just one, the desired servo position, which we get from the numeric control. Then finally, a carriage return and line feed. Okay. That's the command to move the servo. Click the test button to see the message after expressions are replaced by current control values. So that's the message that'll be sent to the Arduino when the send button is clicked. All that's left is to apply the design, which updates the runtime interface panel. After selecting a serial port and opening a connection to the Arduino, I can enter values and press the send button to move the gripper. The monitor window shows serial messages received from the Arduino in black, and messages sent to the Arduino in orange. Now I can figure out the servo position to close the gripper. Looks like 60 degrees is fully closed. And 160 degrees is fully open. Next, we'll look at storing these positions as part of the gripper program's configuration. The set of commands that can be sent to a device are called a protocol. Like any part of a project, there are choices to be made. For example, I want to add buttons to open and close the gripper. There are a couple of ways to do that. First, I could just send raw positions. Or, I could extend the protocol with dedicated open and close commands. The second approach requires a little more work, but employs a powerful programming principle known as separation of concerns. Separation of concerns is a design concept for breaking solutions into logical sections that are easier to understand and manage. Here, that means the user interface can position the gripper using high-level commands, like open and close, instead of building hardware-level details, like the absolute servo positions, into the user interface. This separation lets us use the same user interface and commands on another gripper where open and closed mean the same thing, even if their exact positions are different. It's not wrong to have MegunoLink send absolute positions though. For a quick test setup or at the start of a project, sending commands with low-level data can be the best approach. That's what we did to figure out the servo position range here. MegunoLink interfaces can adapt and evolve as your project progresses. Here I'm going with option 2 so I can show you some more features in our command handler. Okay, let's look at the Arduino code. First, I'll need a couple of variables to store servo positions for the open and closed gripper. To set these variables with serial commands, I'll register them with the command handler. But I'm using add variable instead of add command. Add variable is a shortcut that lets you update a variable with a serial command without writing a separate function. The command handler itself updates the variable when it receives a serial message with the variable name and new value. And it prints the variable's value when it gets the variable name followed by a question mark. Next, I'll register commands to open and close the gripper. The open and close functions use the new variables to move the servo to the right position. Back in the interface designer, I'll add numeric controls and buttons to update the variables. I'm duplicating controls by selecting and dragging them while holding down the control key to save time. Then updating each control's text using the property editor as we did earlier. Clicking the Send button will update the corresponding variable in the Arduino program. The Print button will write the variable value to the serial stream. I'll add new buttons to send open and close commands. And give names to the numeric controls so I can include them as parameters in serial commands. Finally, I'll set the on-click send property for each button. Commands for the send and print buttons use the variable name registered with the command handler. The send buttons get the numeric value from the appropriate control. The print button gets a question mark. Open and close buttons just send the command registered, no parameters for them. After updating the design, the new interface panel lets me set positions that open and close the gripper. I'll use the values we found earlier. Clicking the Send button sends the values to the Arduino, where the command handler updates the corresponding variables. I can check the values with the Print buttons. The command handler prints the variable's current value when it sees a question mark parameter. And finally, I can open and close the jaws with a button. It would have been faster to send raw positions when the open and close buttons are clicked. But by having the Arduino store positions and implementing open and close commands, the same interface can be used for different grippers. However, the position variables are stored in RAM, so their values are lost if the device is reset or its power is disconnected. Next, we'll look at how to save the values in the Arduino's EEPROM where they are retained through reset and power cycles. An EEPROM is a form of permanent memory, generally used for storing settings and built into most Arduino boards. Unlike RAM, where program variables are stored, data stored in the EEPROM is not lost when the Arduino's power is removed or the device is reset. MegunoLink's Arduino library includes a template that makes it easy to store structured data in the Arduino's EEPROM. The first step is to include the header file. Then I'm going to wrap a structure around the variables I want to store in the EEPROM. Structures combine variables and functions so that you can work with them together. Here, we have one structure member for the open position and one for the close position. I'll also add a reset function. The reset function initializes each member variable with a default value. Reset is called automatically by the EEPROM template when it can't find valid data in the EEPROM, such as the first time the program runs or when the structure is changed. The structure defines the layout for EEPROM data but doesn't store anything itself. To store values, I need an EEPROM variable. The structure name goes between the pointy brackets to provide the layout of data in the EEPROM. This variable also keeps a copy of the EEPROM data in RAM. That's accessed through the variable's data member. So, we need to update all references to the old open and closed position variables to use values from the persistent configuration. The persistent configuration variable also provides load and save methods for retrieving and storing data. Values are loaded automatically when the program starts, so you won't need the load method very often. But you must call save to update the EEPROM whenever values are changed. I'll add a new save command and have its command handler function call the persistent config variable save method. And add a new button in the interface designer so the user can decide when to update the EEPROM. Now, when the Arduino is reset or unplugged, the open and closed servo positions are recalled from the EEPROM. Okay, now we have a user interface that can move the servo to an arbitrary position, update configuration, store configuration in the Arduino's EEPROM, and open and close the gripper. There are buttons for sending each value entered to the Arduino. This separation is a common pattern that gives the user a chance to check for mistakes before completing the action. However, sometimes a more immediate response is useful. Next, we'll look at dynamically controlling the gripper position with a trackbar. Trackbar values are changed by dragging the thumb, or by entering values into the attached number control. They can send serial messages when the value changes, although that can generate a lot of serial traffic. So, the control can send just one message, when the user finishes dragging the thumb, if you prefer. Just set the control's delay sending changes property to true. The trackbar looks good for moving the jaws interactively, so I've added it to the gripper controller interface. By default, the control's value ranges from 0 to 100, which is a good range for representing fully closed and open jaws. Controls like the trackbar send the value changed command properties serial message when their value changes. And of course, these messages can include the trackbar's current value. So, this message will send a set gripper position command with the trackbar position. Here I'm sending a new command to set the relative jaw position. Next, I need to register and implement the command in the Arduino program. The new command handler function retrieves the position parameter and checks it is valid. Then, it calculates the absolute servo position by interpolating between the open and closed positions. And, finally, updates the gripper position. And just like that, we have fine control over the gripper. MegunoLink sends messages as the control is moved, which the Arduino uses to update the jaw position. That deserves a round of applause. So far I've focused on sending serial commands from the interface panel to the Arduino program, where the command handler takes an action, such as updating a variable or calling a function. The Arduino program can also send serial messages for MegunoLink to interpret. Serial commands sent to MegunoLink can do many things, including graphing data, updating tables, or playing audio clips to alert you about an event or problem. Next, I'll have the Arduino program update our interface panel with the raw servo position and configuration it retrieves from the EEPROM. This is more convenient than just printing values in the serial monitor. To begin, I'll add a new button. This button will send a new command, get configuration, to ask the Arduino program to update the interface panel. We can't just send the configuration from the Arduino's setup function. Remember, the setup function only runs once, when the Arduino starts. The serial port might not be open and ready to receive data in MegunoLink at that point. One solution to this problem is the serial connection component. It sends messages when a user opens the connection, so could request the configuration automatically. More on that in the documentation. But for now, I'll just use a button. The get button replaces print functionality, so I'll get rid of those two. Let's take a look at the example code window. This window shows example code that you can use in your Arduino program for the selected control. The code shows some of the ways you can send commands to interface panel controls using our Arduino library. As the example shows, you'll need to include the MegunoLink library in your Arduino program, create an interface panel variable, then use the available functions. Most functions take the control's name as the first parameter and a property value for the second. Click the Help button for more details on control properties that can be updated using serial commands. So, selecting one of the numeric controls shows there's a set number function available. As you might guess, this function sends a value from the Arduino program to update the control's value. I'll copy the code I want for the closed position control and paste it into a new function in the Arduino sketch. And do the same for the open position control. Then replace the example values with the actual gripper position stored in the persistent configuration variable. To complete the implementation, I'll include the MegunoLink library, where all these functions are defined. And I need to register the new function with the command handler. Now when MegunoLink asks for the configuration, the Arduino program will call this function, which updates controls on the interface panel. I'm also going to add a new function to update the servo position. The function combines updating the servo and MegunoLink. This will make it easier to send the servo's position to the interface panel every time it's changed. Using the new function in place of servowrite will reduce the amount of program memory needed and the chance of adding bugs as the program evolves. Voila! The position controls are updated from the Arduino whenever the configuration is requested. And the raw position control updates whenever the jaws are moved. Let's look at the output from the force sensor glued to the jaws. The sensor could measure how hard the jaws are squeezing so the motor isn't overloaded and the gripper doesn't crush things it picks up. Let's see if it is sensitive enough. MegunoLink's timeplot is good for understanding sensor behavior. The timeplot graphs values against the time they are received, so you can easily see trends and measurement history. Plots can be added to the interface panel. But creating a separate visualizer is a quicker and easier way to explore a sensor's response. On the Arduino side, plotting a sensor measurement is the same whether the plot is on an interface panel or in a separate visualizer. Create a time plot variable and call its sendData function. The first parameter is the series name and the second is the data value. MegunoLink automatically timestamps the measurement as it arrives at the plot. But don't do it this way. Remember, the Arduino runs the loop function as fast as it can. This loop takes 120 microseconds on an Uno. Sending data every time through the loop would overwhelm the serial channel. And we really don't need that many force measurements anyway. Sending measurements 10 times a second, every 100 milliseconds, is usually more than enough. However, don't use a delay either. Serial commands received while the Arduino is twiddling its thumbs and the delay might be missed by the command handler. The best approach is to keep track of when the last measurement was sent. And send the next one after enough time has passed. The Arduino timer in our library makes this common pattern easy to use and understand. Just include the Arduino timer header file to use it. And just like that, we can see how the force sensor responds to pressure. It looks like a promising approach to detect objects in the jaws and avoid overloading the servo motor. But I'll leave the rest of the implementation for another time. Let's recap the interface panel. Interface panels are built in the Interface Panel Designer by dropping controls onto the design surface and setting their appearance and behavior using the property editor. Properties in the communications group set serial messages, which MegunoLink sends when controls are clicked or their values changed. Use the command editor to build and test commands. Add references to include control values in messages sent to your Arduino sketch. In the Arduino sketch, the command handler processes serial messages. It looks for registered commands, then calls the corresponding function when it finds one. Each command handler function retrieves any parameters from the message and implements the command behavior. The Arduino sketch can update controls using interface panel variables. and store configuration using our EEPROM library. Interface panels can be combined with other visualizers to assemble a custom interface that evolves with your project. We've just touched the surface here. Check out the links below for more docs and the MegunoLink download to start building an interface for your own project. Tap the like button to help others find our content. Then check out this video to see how to install our Arduino library. Or this one to dive deeper into plotting data with MegunoLink.